Welcome to the first episode of the FORCESPRO demo series on path tracking control. In this video, we will show you how to model the vehicle dynamics and formulate and solve the appropriate MPC problem using the FORCESPRO SQP solver. We aim at providing real-time control for vehicle maneuvering in applications such as lane change or passing by a car. This can be implemented in the form of model predictive control, where we regulate the car movement such that it tracks the predefined trajectory in real time. For this specific application, we will look at the prediction and control horizon of length 10. The vehicle is modeled using the traditional kinematic bicycle model, encompassing both lateral and longitudinal vehicle dynamics. Note that the specific MPC formulation depends on the difference between temporally and spatially resolved formulation. The system dynamics are therefore represented with a fifth-order nonlinear model, with state variables being the 2D car position in Cartesian coordinates, car velocity, heading, and steering angle. The control inputs are the acceleration force and steering rate, while the parameters are the car mass and distances from rear and front wheels to the center of gravity. In terms of the control objective, the goal is to drive the car as closely as possible along the desired trajectory of path points. In addition, we want to avoid excessive maneuvers in order to ensure ride comfort. This is achieved using the stage-wise least square cost function with 4 terms. The first 2 terms penalize the deviation along the x and y axis from the prescribed path, whereas the last 2 terms minimize the use of control action. Furthermore, we will employ a Gauss-Newton-Hessian approximation since it is highly efficient with least square objective functions. We will now briefly go through the pseudocode of the function used for solver generation with FORCESPRO high-level interface. First, we define the I-struct with indices of different state and control variables, followed by problem dimensions. Note that we will have 2 runtime parameters due to waypoint coordinates used for path tracking. The objective function is defined using the FORCESPRO model.ls objective, which provides a handle to a previously defined least square objective. We will also provide a terminal objective with increased costs for the last stage. Similarly, the dynamics are defined using equality constraints with function handles to the previously defined continuous dynamics function. Here, we also denote the indices of states and control inputs, as well as the integration step using the explicit Runge-Kutta-4 integrator. Inequality constraints are only composed of lower and upper bounds on all decision variables, and initial conditions will be prescribed for all state variables. Next, we initialize default solver options and redefine few general ones. For instance, we set the maximum number of iterations to 200, we set the logging level of the FORCESPRO solver to 0, and decide not to automatically build a Simulink block of the solver after it has been generated. We will try 2 different FORCESPRO NLP solvers. First, an SQP NLP solver with Gauss-Newton-Hessian approximation and 1 QP solved per qual. Secondly, we will solve the problem using a PDIP NLP solver and the default BFGS Hessian approximation. Finally, we can generate the appropriate NLP solver and run the model. The 2 solvers result in almost the same control performance, as showcased here. The green and blue line are the predicted and past trajectory. Red line is the desired path, and dark crosses are the waypoints. The car clearly follows the racetrack with prescribed accuracy, and all system constraints are well respected. In terms of computational efficiency, the SQP NLP solver takes 1 iteration and approximately 0.2 milliseconds to solve the problem, whereas the PDIP NLP solver takes 17 iterations and around 0.48 milliseconds on average. Considering that there is a negligible difference in control performance, that is, all system bounds are respected, one can argue that using a single iteration of the SQP NLP general solver is the more efficient option for this specific control application. With this, we conclude the modeling part of the path tracking demo. In the next video, we will show you how to run the actual code for generating the SQP general solver provided with your FORCESPRO client.